Welcome to the webinar series of SAR data processing. In today's webinar, we will see the SAR data processing concepts. Okay, so this SAR data processing has been divided into two webinars. First is SAR data processing 1 and SAR data processing 2. Myself, Ashish Joshi, I am working as a scientist at Programmatic and Remote Sensing Department, IIRS, Dehradun. So in this webinar, the basics of the radar and SAR concepts we will learn, in which we will learn the linear frequency modulated signal, which is also called the LFM signal, pulse compression techniques, range and azimuth resolution, synthetic aperture concept, Doppler centroid, range cell migration, which is called the RCM. After that, we will see the basics of SAR image formation, which is also called the level 0 processing, in which we will see the range compression, RCM correction, and the azimuth compression. Now, what is the basic difference between the optical and SAR data processing? So in this slide, we can see this is the optical image, and after some data processing, this is the optical image which is undergoes through the LTC correction, which is one radiometric correction. So one can see in this optical image, in the raw data, we can see the features. Okay, but in the SAR image, this is the raw data of the SAR image, then we are not able to perceive any features in this image. Okay, so this is the optical raw data and this is the SAR raw data. So we are doing some processing in the optical image, which is called the LTC correction, and the image looks like this. So in this image, we can see some of the stripes are there, which is due to the CCD, charge coupled devices. But in the SAR, we are not able to perceive anything. We cannot find any feature. So in the case of SAR, we have to do some signal processing. Okay, so with the help of the signal processing, we are focusing the image, and after the SAR data processing, the processed image will be look like this. Okay, so this is the basic difference between optical and SAR. Means in the optical, we can see some of the features in the raw data, but in the SAR raw data, we cannot see any of the features. And we have to do some of the signal processing technique in the SAR data processing. Okay. So before going to the SAR data processing concept, we have to see some of the radar and SAR concept. So what is the radar? So radar transmits the microwave electromagnetic radiation pulse towards a scene through the transmitter. Means radar has one transmitter which transmits the microwave electromagnetic radiation. Since it is a active device, so it transmits itself. Okay. Then this pulses interacts with the Earth's surface and back scattered towards the radar antenna receiver. So these are the pulses. So through transmitter, it is transmitting the electromagnetic pulses, and these pulses interacts with the Earth's surface, and that back scattered pulses are collected by the SAR, and this distance is called the R or the slant range. Okay, so it observes the strength, which is called the detection, or the backscattered energy, and the time delay of the return signal. So it will have the strength means detection part and the range. So it measures the range also and the energy also. And this range is calculated through the formula time is equals to distance upon speed. So time delay is given by 2r by c, because these electromagnetic radiations has traveled twice this distance, this r, then twice of this distance it has traveled, so it is 2r. So total distance is 2r divided by the speed of light, because the electromagnetic radiations or pulses travels with the speed of light. So the formula is time delay is equal to 2r by c. So the range can be calculated as CT by 2. Okay, so this is the range formula which we can get from the radar. So range is calculated through the time delay. So this is the first basic concept, means the range can be calculated through the time delay. What is the time delay between from the transmission to the reception? Now, antenna is the device that directs the electromagnetic radiation emitted from the transmitter to a desired direction in space. Okay, so what is the role of the antenna? Means it will transmit the electromagnetic radiation towards a particular direction. Okay, so this is the antenna. It will contains the transmitter and the receiver. Okay, so that is called the radar beam. So it is the radar beam and it has some of the angle. So this angle is called the beam width. Then this beam width is called the theta is equals to k lambda by l. Okay, so theta is equals to this wavelength by l. This is the wavelength and this is the length of the antenna. Okay, so this antenna can be a parabolic antenna or it can be a phased array antenna. Okay, so this if it is a parabolic antenna, then this L can be replaced by the radius. If this antenna is a phased array antenna, then this is and this length of the antenna is of rectangular form. Okay, so that phased array antenna is of form rectangle. Okay, so this is called the radar. And how it illuminates the earth surface? It illuminates the earth surface like a torch. In with our daily life we are using the torch and we are illuminating a surface to the torch. In the same way radar is illuminating the earth surface with the microwave energy. Okay, here it is the optical energy, means light energy it is passing. Okay, in the radar it is using the microwave electromagnetic radiation and it is an active sensor, so it is using it to illuminate a particular surface. Okay, and the radar beam can be viewed as the cone. So since no antenna is perfect and some of the radiated power is transmitted outside the main lobe, so if it is a travel direction and this is the radar, this is called the main lobe. Okay, so when it will illuminate the surface, the main beam will form the footprint from this beam. Okay, and this is the sum of the side lobe. Okay, so the radar signal decreases with the distance according to 1 by 4 pi r square. Okay, so when the radar signal travels through the space, then their energy will decrease from the formula 1 by 4 pi r square. And in the same way, when it is returning, it is also decreases by 1 by 4 pi r square. So the received signal is about 15 times weaker than the transmitted signal. Okay. So in the space we are transmitting any signal, then the received signal is 15 times weaker than the uh, transmitted signal. Okay. So this is the sum of the radar concept. So what is the synthetic aperture radar? So synthetic aperture radar is also be known as the imaging radar. So simple radar cannot produce any images, but the synthetic aperture radar produces the high resolution images. So SAR is a side looking radar system which makes a high resolution image of the earth surface. The continuous strips of the ground surface are illuminated to one side of the flight. Means if it is a SAR, then it flowing in this direction and it is a side looking and it will illuminate the surface like this. This is called the look angle. The signal is recorded and digital signal processing techniques in the ground are used to focus the image and obtain the high resolution images. Okay, so digital signal processing techniques are uses for processing the SAR data. So this um, way the raw data is formed, means as the signal is, as the SAR is moving from this direction, then it will form the image like this. Means it will have one return pulse, receive pulse of first pulse, second pulse, third pulse, and this way all the pulses are added. So this is called the range and this direction is called the azimuth, and the SAR raw data will look like this form. Okay, Now, normal optical has the one resolution, but the SAR has the two resolution. One is called the range resolution, and second is called the azimuth resolution. So the fine range resolution in case of SAR is achieved by using the pulse compression technique, and the fine azimuth resolution is achieved by using the synthetic aperture combination. So a combination of two principles enables the high resolution image in both range and azimuth direction. So originally radar cannot produce a high resolution images. So what we will use two concepts. One concept is the pulse compression technique, and second is the synthetic aperture concept. So these two concepts will enable to have a high resolution in both the directions, means in the range direction and in the azimuth direction. So now we will learn what is the pulse compression technique. So basic terms of the electric magnetic waves are the wavelength. If this is the electromagnetic wave, then the distance between two crusts is called the wavelength. The frequency is the number of crusts that passes through a fixed point in a given amount of time. So that is the frequency, which is related to C is equals to lambda nu. Okay, so nu is given by C by lambda. The pulse width is the time duration of the pulse, how much time it has traveled. That is called the time duration of pulse is the pulse width. What is pulse remitting in a frequency? The number of pulses transmitted per second, means in 1 second how much pulses we are transmitting. So that is called the PRF or pulse repeating frequency. Pulse repeating interval is just the inverse of the PRF, means PRI is equals to 1 by PRF. So time between the two pulses is called the PRI. Okay, so pulse repeating frequency is the how much pulses we are transmitting per second, and pulse repeating interval is the time between the two pulses. The sampling frequency, the frequency at which the pulse is sampled for the conversion of pulse from analog to digital. Okay, so when we are converting the pulse from the analog to digital, then we have to use some of the sampling frequency. We have to sample the data. That sampling is called the sampling frequency. The formula is given by, means number of samples is given by the sampling frequency into the pulse width. So while converting the analog pulse to the digital form, we have to use some sampling frequency, and how much number of sample we will get is depend on the what is the pulse width and what is the sampling frequency. So this is the one of the pulse. So this is the low frequency and this is the high frequency. So in this low frequency we can see this lambda is high, means the distance between two crusts is higher, so that is called the low frequency. And in this high frequency this distance is lower, so lambda is lower for the high frequency. So this is the formulation for any electromagnetic wave, means exponential of I into phase. This phase is given by the 2 pi the carrier frequency into the time taken. So now how to get a better range resolution in case of SAR. Okay, so there we can understand. So this is called one pulse. So this is the pulse width. Okay, so this is the first pulse, the second pulse, third pulse. So it is called the transmitted pulse. Okay, now first, second, third, fourth, and this is called the reception window. Okay, so means in this window we will receiver will receive the pulse. Okay, so and the time between two pulses is called the PRI. So this is called the this pulse and this pulse. It is called the PRI, and PRI is given by 1 by PRI. So in if this is the pulse and this is the receiving window, so we can see this one, means in this time interval we have first this pulse and this pulse, and in between if two targets are there, T1 and T2. Okay, so this will receive in this received window. So these two pulses will be received in this reception window. So what is the time difference between the, transmitted to the first target? It is 2r by c, which is given by the first from the formula of the time delay. So this is the time from the first pulse, and this is for the second target pulse, 2R2 by C. Okay, so this is for the first pulse, and this is for the second pulse, means first target and second target. So if this difference means these two target will be differentiated by this SAR when this distance is greater than the pulse width, or we can say the pulse width should be lesser than this time interval. Means if pulse width will be lesser than this time interval, then only the SAR can distinguish these two targets as separate two targets. Okay, so this is the formula. Tau should be lesser than the difference of this means 2C by R2 minus R1. So this is the formula which will be we will use for the range resolution. So if we have the tau, say we can have the tau of 20 microsecond. Okay, so if we use this tau 20 microsecond, then how much is the delta R? Delta R is coming like 3000 meter or 3 kilometer. So the sensor will separate two targets if distance between them is equal to or greater than 3 kilometer. Means if we use tau as 20 microsecond, means very short time with 20 microsecond, then also the range resolution is coming like 3 kilometer. It will discriminate two targets if the distance between the two targets is 3 kilometer. Okay, so this is the two target 1 echo, target 2 echo, and it is called the combined echo. Okay, so the SAR will distinguish these two targets as separate targets if the delta R is 3 kilometer. But this is very much coarse resolution. So our problem is to how to get a fine range resolution. Now one solution is if delta R, this is the formula, delta R is greater than C tau by 2, then if we decrease this tau, so if we decrease this tau, then delta R will decrease. So we can get a very small range resolution. But from the formula, power is equals to PT into tau into PRF. This is the formula of the power. So if we decrease this tau, if we decrease this tau, then the average power will be reduced. Okay, so we cannot decrease the tau up to some certain level. Okay, so it will reduce the energy in the pulse. If we reduce tau, then it will reduce the energy in the pulse. Then what is the solution? Now the solution is called the linear frequency modulated signal. Okay, so what is that? Means and this is the electromagnetic pulse with the frequency fixed frequency. So LFM is a longer pulse with varying frequency. Okay, so this is the fixed frequency pulse, and this is the uh, uh, pulse with the varying frequency. Okay, so in case of LFM, the frequency F0 is not kept constant, but it is linearly changes from F0 to F0 plus delta F. Okay, so in this case, the frequency will be constant, but here the frequency will be varying. Okay, so bandwidth is given by the F0 by delta F minus F0, means some delta F is the increment. So F0 plus delta F minus F0. Then the bandwidth is given by delta F. Okay. So bandwidth is independent of the pulse width. So this bandwidth is independent of pulse width, means we can make a pulse which is independent of tau. Okay, so only with the help of bandwidth we can make a signal. So pulse with large bandwidth can be constructed. Okay, so a pulse compression technique is used to get a better resolution. So this is the LFM. Okay, so this is called the real part of the chirp. Chirp is also called the LFM. So this is the another name of the LFM signal, chirp. So this is called the real part of chirp, and this is called the imaginary part of chirp. Phase is given by the tan inverse of imaginary part by real, and the frequency is called the d phi by dt. Means if we difference this phase with respect to time, then we will get the frequency. Now if we differentiate this term, then what is we are getting, this is a straight line. So this frequency is linear in nature. That's why we are calling the linear frequency modulated signal. So this is the real part, this is the imaginary part, and we calculate the phase out of it and find the frequency. Then this frequency is coming out as a linear. So what is the pulse compression? So in pulse compression, an expanded pulse, which is called the LFM, is transmitted and later compressing it to a desired resolution in the signal processor through the match filtering technique. Means in our SAR processor, in SAR data processing, what we will do, the first we will create a LFM with the varying frequency. Then this LFM in the SAR processor is compressed to the match filtering technique. Okay, so what is match filtering? We will multiply that signal with the complex conjugate of it. Okay, so if we multiply that signal with the complex conjugate, then we can compress that pulse. Okay, so this is called the reference signal, which is the LFM we are transmitting. And then what we will do, we will do the correlation, means we will multiply with the complex conjugate. We will multiply this complex conjugate of this one, then this output signal is like this one. So we are getting the very fine range resolution. And in this second target also we will get a very fine resolution, and then we can very much differentiate between the two targets. So the target is compressed and represented by the impulse response. So this is also called the impulse response. So what is it means in the pulse compression? If LFM is multiplied with its complex conjugate, which is also called the match filtering, then we can get a very fine range resolution by compressing this target. So this is called the pulse compression. So the how much is the resolution we are getting? So the from the formula C tau by 2, now the LFM is not dependent on the pulse width. So that and the formula of tau is equals to 1 by B. So we will just put this tau as 1 by B. Now the range resolution is given by the bandwidth. Means if larger the bandwidth, then smaller this value. Okay, so like bandwidth of 250 megahertz will give the range resolution of around 0.6 meter. Okay, so we can see if the bandwidth is increases, the resolution is increases. For the bandwidth of 75 megahertz, the resolution is 2, and 150 is getting 1 meter, and for 750 we are getting a 0.2 meter resolution. Okay, so these are some of the formulas for different bandwidth. We are getting different resolutions just from the formula of range resolution is equals to C by 2B, and using the technique of pulse compression. Now we are getting the better resolution in the range direction, but what about in the azimuth direction? The azimuth resolution corresponding to nearest separable points in the azimuth direction. So now our problem is to find a high resolution in the azimuth direction. So for case of simple radar, the azimuth resolution is given by the azimuth beam width into the R, or azimuth beam width already the lambda by L from the formula in R. Okay, so from this formula what we are getting, if we put R is equals to 800 kilometer, means our space-borne satellite in the low Earth orbit, it is around R is 800 kilometer. Lambda is 3 centimeter for the C-band SAR, and L length of the antenna is 12 meter. So how much that azimuth resolution we are getting? Around 2 kilometer. So which is also very much coarse. Okay, so how to get a bit better resolution in case of azimuth side? Okay, so but we can see in optical scenario we can get a higher resolution. But why? Because in the same formula work in the optical sensor also, but there the lambda is very much low, in the order of 0.4 micrometer. Okay, so in the optical case, that beam width is given by the 1.22 into lambda by d. This is the from the formula, from the lens it is coming. Okay, so d is the lens aperture and lambda is the optical wavelength. So optical wavelength in case of the optical sensor, it is given by 0.4 micrometer. D is given by 50 centimeter, and R is around 800 kilometer. Then we are getting up to 0.7 meter. So in the optical scenario, the same azimuth resolution we are getting as 0.7 meter, but in case of microwave region, it is going towards 2 kilometer. Okay, so for that one, we have to use some concept to get a better azimuth resolution. So if we consider how much antenna length is required to have a azimuth resolution of 0.6. Okay, so we can have this formula. So how much antenna length is to achieve the azimuth resolution of 0.6 meter? So what in the formula of this one, L is equals to lambda R by azimuth resolution. If we put this azimuth resolution at 0.6, lambda as 0.03 means 3 centimeter, and this is the R. So L is coming around 40,000 meter, means 40 kilometer length. So what is the antenna length of the radar or SAR? If we have the azimuth resolution of 0.6 meter, means if we want to have a resolution of 0.6 meter, what is the antenna length requirement is 40 kilometer. So it is a very much big antenna. So this big antenna we cannot carry in the space. So we have to have something a different technology to have a better azimuth resolution. So the improved azimuth resolution is achieved by the synthetic aperture concept. Okay. So in the range resolution, what we have used the pulse compression technique, and in the azimuth resolution, we are using the synthetic aperture concept. Okay. So now the radar is converting to the SAR, means synthetic aperture concept is we are using. So what is the synthetic aperture concept? In synthetic aperture concept, a long antenna is virtually made through the motion of radar. Okay, so through the motion of this radar, we are virtually creating a long antenna. Okay, this technique based on the fact that target stays in the beam for a significant amount of time. So in this figure, we can see this target is illuminated by this radar beam, and it is stays in this the beam stays in this target for a quite significant amount of time. So and this target is virtually is seen by the means multiple radars. Okay, so target is observed by the radar from multiple location along the satellite path. So it is observed by the multiple locations. Okay, so azimuth resolution is improved using the synthetic aperture technique. LFM signal is formed in the azimuth direction by the motion of the SAR. Okay, so in case of SAR, the LFM in the azimuth direction is formed through the motion of the SAR. Okay, so in the range direction, because it is an active signal, active sensor, so it is transmitting the LFM signal for the getting the better range resolution. But in the case of the azimuth direction, it is used the motion of the SAR, and it is simulating a larger antenna um, for getting a better azimuth resolution. And the motion of the SAR will form a LFM signal, linear frequency modulated signal, in the azimuth direction. So this is called the synthetic aperture concept. So, in the synthetic aperture concept, this target is seen as a multiple location of the SAR. Okay. Then a array of antenna is equivalent to the single antenna moving along the array line as long as receive the signals are coherently recorded and added. Okay, so this multiple location of the radar will have behave like a long antenna. Okay, it is behaved as a long antenna as these signals are received and coherently added. Okay, so coherently added means the phase of every uh, antenna pulses will be the same. Okay, so this is the synthetic aperture concept. Okay, so means with the motion of the SAR, we are simulating a larger antenna. So this synthetic aperture length is given by the 2 lambda r by L. Okay, so this if we put the formula, then the synthetic length is given by the 4 kilometer. Okay, so from the formula we are simulating a 4 kilometer long antenna by the synthetic aperture concept. So how much is the improved azimuth resolution now? Now the same formula lambda by ls. We are substituting ls as the synthetic length. Now this synthetic length is given by the 2 lambda r by l. Okay, so this formula we are getting lambda r. We will substituting this ls here. Then the length of the antenna is the 12 meter. Then the azimuth resolution is given by the L by 2. Okay, so if the SAR antenna is of length of L, then the azimuth resolution is given by the L by 2. So the length of antenna is 12, then improved azimuth resolution is given by the 6 meter. So this is the case of the strip mode SAR. In the strip mode SAR, the azimuth resolution is given by the formula L by 2. Okay. So in the range direction, it is C by 2B, and in the azimuth direction, it is L by 2. From the concept of the synthetic aperture. In the synthetic aperture, the antenna is simulated by the motion of the SAR, and the azimuth resolution is given by the L by 2. So now summary of the sum of the points. First is LFM is a longer pulse with varying frequency. High resolution in SAR is achieved by the pulse compression and synthetic aperture concept. SAR range resolution depends on pulse bandwidth C by 2B. SAR azimuth resolution depends on the antenna length L by 2. Radar azimuth beam width is given by lambda L, and radar azimuth resolution is given by lambda R by L. So these are some of the concepts. So one of the concept in the SAR is effective velocity concept. In normal SAR geometry, this orbit path is also like this, which is not linear in nature, and Earth surface is also some oblateness is there. Okay, so this is the concept of the normal satellite scenario, in which this is the satellite velocity, this is the r, and this is the r0. So for the simplicity and for the mathematical modeling purpose, we will assume the satellite orbit as a single straight line and Earth surface as plane. And we will derive some of the mathematical relationship. So this is called the rectilinear geometry, and this is called the curved Earth geometry. Now we will have assumed like the rectilinear geometry, then the satellite velocity is replaced by the relative velocity, which is called the VR, which is called the effective velocity. So in the rectilinear geometry, this velocity is replaced by the effective velocity, and this effective velocity is approximately is equals to Vs into Vg. Vg is equals to velocity with which the beam moves along the ground. Okay, so but at which velocity the beam is moving along the ground, or what is the ground speed. So this is given by the Vg. So this effective velocity is given by the root of Vs into Vg. And this range is given by the R0 by VR eta square. Okay, so from this Pythagoras theorem, just we are applying. There's R is given by R0. This is the range of closest approach, and R0 plus VR by eta square. So and this is called the hyperbolic equation. So this is the main equation which will be used for our SAR data processing. So this is the hyperbolic equation, means the range is given by the R0 plus VR eta square. VR is the effective velocity, and eta is the time of approach. Okay, so how the image is formed as the SAR is moving. So this range is not is in the same straight line. It will follow a hyperbola. Okay, so in this slide we can see as the SAR antenna is moving, the target signal how it is writing. It is writing as a hyperbola. Okay, so we have to correct this correction. So this is called the range cell migration. Okay, so like this is the range cell are migrating, means it is not writing into this straight line like this, but it is migrating towards the hyperbolic surface. Okay, so this RCM effect need to be corrected during the SAR data processing. Okay, so this is the called the range cell migration, in which the target is not right in a straight line, but in a hyperbolic way, in this direction. So we can see in the RCM effect in the image, like, and this is the target history of a any target. So it is writing in this way in the SAR image. So next is the Doppler effect. What is the Doppler? Now, due to the motion of the SAR, we have already learned the Doppler. Doppler, what is Doppler? When an observer moves with respect to the source, a shift in frequency is observed, which is known as the Doppler frequency. Okay, so this Doppler shift is given by this formula. Fd is equals to 2Vs sine squint of lambda. So this is the Doppler shift. So in this diagram, we can see as this truck is approaching to this observer, so it is observing with higher frequency and it is observing with the lower frequency. So in this way, LFM is made in the azimuth direction due to the Doppler. So this is called the LFM in the azimuth direction. What I have told, the LFM means a wave which have the variable frequency. So in this case, the variable frequency is made due to the Doppler effect. Okay. So what is the squint angle? Squint angle is the angle made by the slant range with respect to the zero Doppler plane. Okay, so this, if it is the, like, it is showing exactly in the in this direction, then it is called the zero Doppler, means it is seeing the exactly to this position. But if it is seeing in this direction, means it is here it is the zero Doppler, and what is the angle it is making? It is called the squint. So this is called the squint angle if it is making some angle with respect to the zero Doppler. Okay. So we have both the positive and negative Doppler shift. As the radar flies over the target P, means as the radar is moving here. So first the it has the positive Doppler shift, means first it is will be a positive Doppler shift, then it will become zero, and then negative Doppler shift. Okay, so this is the Doppler characteristics of any target. Means as the SAR sensor moves over the target, means if it is there and target is there, then first it will be the positive, means the frequency will increase as it approaches towards the target. Here it is becoming a zero, it is called a zero Doppler, and then it will become a negative. Okay, so from here to here, this is the Doppler history, means first the Doppler will be positive and then negative. Due to this changing in the frequency, Doppler frequency, we are getting the linear frequency modulated signal in the azimuth direction. So here, what is now, one concept is called the Doppler centroid. Okay, so we have understood what is the Doppler. Now, what is the Doppler centroid? Doppler centroid is defined as the Doppler frequency subtended by the target at aperture center. Means what is the frequency at this center? As the during the synthetic aperture formation, as the this radar is passing from here to here, so what is the frequency at this location, means at the aperture center. So this is the aperture, it is forming synthetic aperture. Then what is the frequency at aperture center? It is called the Doppler centroid. Okay, so this is the Doppler frequency curve, and here we can see this is positive and this is negative frequency. It is increasing from here, it is become positive, then zero, and then negative. And what is the frequency? It is exactly it is having, which is called the Doppler centroid. So basically, due to the limitation of the PRF, we have two terms in the Doppler centroid. One is called the Doppler ambiguity and one is called the base point centroid. Means if we have the absolute Doppler centroid, means we are getting some of the Doppler frequency as 9,500 Hertz, but our PRF is 3,000. So these frequency will be aliased, means it will be aliased in the multiple of this PRF. Okay, because our spectrum is like of 3,000 Hertz only. So our, if our Doppler centroid is greater than this 3,000, then there will be aliasing. Okay, so what we have to do, we have to find at which factor it is aliased. So these two, the formula is absolute Doppler centroid is equals to Doppler ambiguity into PRF. Okay, so this is 3,000 and this is 9,500. So Doppler ambiguity will be 3. Means 3 into 3,000, it will become 9,000. plus base Doppler, it will be the 5000 hertz. Okay, so this is called the base Doppler centroid, and this is called the Doppler ambiguity, means at which time it is folding over. So 3 times it is folding. Okay, so absolute Doppler centroid has two parts. One is called the Doppler ambiguity, and this is called the base Doppler centroid. So this is called the base Doppler frequency, and Doppler ambiguity means how many times it is a multiple of PRF. So that we have to estimate the Doppler centroid in our SAR processing. So it can be estimated either through the geometry by this formula or through the image itself. In the image-based method, the frequency of the peak of the Doppler magnitude is estimated from the power spectrum of the data. Means if we have the raw data, we have to find out the power spectrum of the data, and after finding the power spectrum, where is the peak is coming, we will find the FDC location. What is the peak of the power? That is called the Doppler centroid. Means power spectrum means we have to take the FFT, and then we have to find the absolute of that data. Then we can find out the Doppler centroid. Now what is zero Doppler plane? Okay, so in all SAR data processing, we will use the zero Doppler processing. So if this is the SAR, and this is the slant range. Okay, so this is called the beam footprint. So SAR processing is done on the zero Doppler plane. So slant range is the distance between the SAR range target, and squint angle is the angle made by the slant range vector with respect to the zero Doppler plane. So this is the range vector, and this is called the zero Doppler plane, means which is perpendicular to the motion of the sensor. What is zero Doppler plane? Zero Doppler plane is the plane containing the sensor that is perpendicular to the sensor velocity vector. So this is the motion of the SAR, and what is the perpendicular? This is the zero Doppler plane. Okay, so this is the range, and then what we have to do, we have to do the processing in the zero Doppler plane. So we have to transform this plane in this plane. Okay, so we have to find this R to the zero Doppler plane. So this is called the R0. So that is slant range after processing. So this is the R, which is the before processing, and this is the R0, which is the after processing in the zero Doppler plane. So this is also called the range of closest approach. So SAR processing is done in the zero Doppler plane. Okay, so this is the ground range after processing to the zero Doppler. So this is the normal range. After converting into the zero Doppler plane, the range becomes the R0. So our SAR imaging coordinate system has two coordinates. One is range and one is Doppler. So optical sensor has angle format. Okay, so everything will be done in the form of the angle. Radar has angle and time delay format. So we have their angle and time delay in case of normal radar. But in case of SAR, we have time delay concept and Doppler concept in the case of the azimuth direction. So in every pixel have one range and one Doppler value. From that 2 points, we can focus any target, because every target has unique range and unique Doppler, and we can differentiate each target as different range and different Doppler based on the SAR processing technique. Some of the signal processing concept is time domain is converted to frequency domain through the Fourier transform. Means if we want to transform the time domain to the frequency domain, what we have to do, we have to take the FFT, which is called the fast Fourier transform. Transmitted SAR signal convolved with targets and return back to the receiver. So normally in our time domain, means how the signal is captured in the SAR, means SAR transmitted a signal, it is interacting with a target. So while interacting, the mathematical model, what we are assuming that it is doing the convolution with the target. So that is called the convolution. Okay, so in the time domain. So and the formula is convolution in the time domain is equals to the multiplication in the frequency domain. So if two signals, this ST and ST, are convolving in the time domain, then if we will take the Fourier Fourier domain, FFT means if we transform in the frequency domain, then we have to just multiply these two signals. Okay, so but our assumption is in the time domain, the SAR signal is convolving with the target signal. Okay, so if this is the ST is our transmitted SAR signal, and ST is the means target in the earth surface. When these two targets is convolved in the earth surface, then if we will take in the frequency domain, then we have to just multiply. Okay, so most of the SAR processing we will do in the frequency domain, because in the frequency domain the mathematical equations are easier to use, means we have to just multiply these two signals. Okay, so these are some of the signal processing concept, means we are doing the every signal processing in the frequency domain in the SAR, because it will take the lesser time, because the mathematical calculations are simpler to use in the frequency domain, while in the time domain it is very much time consuming for the SAR processing. So these are some of the summary of what we have read. In slant range is the distance between SAR and target. Squint angle is angle made by the slant range vector with respect to zero Doppler plane. Zero Doppler plane is the plane containing the sensor that is perpendicular to the sensor velocity vector. Target trajectory migrates through the range cells due to the motion of the sensor. This is called the range cell migration. Doppler centroid is given by this formula. Time domain is converted to the frequency domain through the Fourier transform. Convolution in the time domain is equals to the multiplication in the frequency domain. Okay. Now we will go to the SAR data processing. Once you have understood the concept, means one is the LFM concept, synthetic aperture concept, RCM. These are some of the concepts in the SAR data processing. Now we have to process the data, means we have to do the compression in the range direction and azimuth direction, and do the RCM correction also. Okay, so how to do? Then first the raw data we will take. Raw data is in the form of the complex. First is the range compression, azimuth FFT we have to take, then RCM correction, azimuth compression, and then azimuth IFT, means inverse FFT we have to take. Then the focus data we have to give. This process is called the range Doppler algorithm for the low squint. Low squint means it is have the very much low squint angle. So this is the raw data. After the SAR data processing, it is the focus data. So what we have to do, we have to do the range compression and azimuth compression using the pulse compression technique. So what I have told, like pulse compression technique, what is that? We have to multiply the signal with the complex conjugate. So here also in the SAR data processing, we have to multiply the LFM with respect to the range direction and with respect to the azimuth direction. In the range direction, we have all the system parameters. In the azimuth direction, we have to estimate the parameters. So how the SAR raw data means, it will contain one real part, one imaginary part. So amplitude is given by, if we take the square root and the real square plus imaginary square, then the amplitude is given, and phase is given by the tan inverse of imaginary by the real. So SAR data signal is in the form of A into exponential of J phi. A is the amplitude and phi is the phase. Okay, and A square is called the intensity or power. If we take the square of the amplitude, then we will get the intensity or power. So this is the SAR raw data. The first what is we have to take, we have to do the range compression. So in the range compression, first we have to uh, make the match filter. Match filter means we have to means this is the match filter we have to make J pi KR T square. So this is the match filter we have to make. So KR is called the range chirp rate, which is given by the B by tau. So the SAR parameters is already given by the SAR data, means we know the pulse duration. What is the pulse duration? Bandwidth, sampling rate, light velocity, and chirp length. So for the we know the pulse duration, it is 27 microsecond, and bandwidth is 28 megahertz and 32 megahertz, and light velocity is this one. So how many samples in the range direction we can find out, means how much chirp length will be the length. It is given by the B into tau, means bandwidth into the tau. So which is given by 756. Okay, so this is called the match filter. We can make this kr is called the range shift length, which is called the b by tau. So what we have to do, we have to multiply this match filter in this data. If data is coming, we have to multiply this in the range direction. So this is called the reference lfm. So this lfm is multiplied in the range direction. Okay, so what is the range compression? In the range compression, FFT in the range direction of the SAR data we have to take, means first we have to we have to make the SAR data in the frequency domain. Okay, so we have to take the FFT in the range direction, means one direction FFT we have to take. Then FFT of the transmitted LFM pulse system perform, means we have to first take the data FFT. Then what is our reference signal? That is our reference signal which we have made based on the SAR parameter. So that we have to take the in the frequency domain. So both signal we have to do in the frequency domain. How we have to do? We have to take the FFT, means FFT in the range direction of the data and FFT of the transmitted LFM. Then we have to just multiply, means we have to do the match filtering, means multiply the conjugate of the LFM with the raw data in the frequency domain. So what we have to do, we have to take the complex conjugate of this LFM pulse and just we have to multiply, just multiplication we have to do. After that we again go to the time domain. Now how to do go to the time domain? Just we have to do the inverse FFT. Okay, so in this inverse FFT, we have to do and we have to go back to the time domain or the range domain. So if this is the raw data, so this is the range compression data. It will look like. Okay, so this is called the RCM effect. You can see this is not a straight line, but it is a curve line. Okay, so this is called the RCM effect. So we have to correct it. So in the range cell migration, what we have to do, after the range compression, and azimuth FFT is performed to make the range Doppler domain. So we have to do the RCM in which domain? Range Doppler domain, in which we in the azimuth direction we have to take the FFT, means in the in one dimensional FFT we have to take in the azimuth direction. Then the RCM is performed in the range Doppler domain. All target trajectory in the same range are transformed into the single target trajectory through the interpolation. RCM makes the trajectory straight so that they become parallel to the azimuth frequency axis. Doppler centroid estimation can also be done in this range Doppler domain. So what we have to do after the range compression, we have to take FFT in this direction. And after that, we have to do the interpolation. So in this axis, what we have to do, we have to do the interpolation in this domain. And we have to make this all curve into a single straight line. So after the RCM correction, this range compressed data will be look like this one. So this is the RCM corrected data. So we have to do in the range Doppler domain, means we have to take the FFT in the azimuth direction and then we have to take the interpolation. Now what we have done the range compression and we have done the RCM correction. RCM is done through the interpolation and range compression is done through the pulse compression technique. Now in the azimuth direction, what I have told, due to the Doppler, one LFM will be we have, and this Doppler shift is directly proportional to the radial velocity. What is the radial velocity? This R is this slant range. Then RT is given by the R0 by plus this formula. Okay, so this Doppler shift is proportional to the radial velocity. So the phase is formed using this formula 4 pi by R. So R is given by this formula and phase is given by this. So now what we have to do in the pulse compression, what we have done in the range direction, the range direction we have make a match filter which have this formula in the range compression, means KR range triplet we have used B by tau. In the azimuth direction, we have to use the azimuth FM rate, which is given by Ka, which is dependent on 2 VR square by lambda R0. So we have to make a LFM in the azimuth direction, which is called the match filter this way. Okay, so this match filter, what we have to multiply in the azimuth direction. So this K mainly depends on the effective velocity and lambda R0. Okay, So what we have to do in the azimuth compression, after the range migration correction, match filtering is performed in azimuth using the match filter with FM rate K. In azimuth compression, azimuth FFT is performed in the azimuth direction. Okay. A LFM pulse is constructed with azimuth FM rate and FFT is performed. So after the RCM correction, azimuth FFT is performed in the azimuth direction. Then raw data is multiplied with the azimuth LFM and in azimuth direction in the frequency domain. Then again we have to do the inverse FFT. Okay, so again what we have to do, just in the frequency domain in the azimuth direction, we have to make one match filter and we have to do the match filtering, means complex conjugate we have to multiply with the data, and the formulation is given by this one. So we have performed three steps. One is range compression. We have to do the uh, that is RCM correction, and we have to do the Doppler centroid estimation. This is called the Doppler centroid. F eta C is the Doppler centroid estimation, and with some of the parameter of VR and R0, we have to make a azimuth direction match filter. And just we have to do the pulse compression technique in both range direction and in azimuth direction. Now, after the processing, this is the raw data and full raw and Doppler algorithm we have applied, and this is the focus data. Okay. So, what are the main points to remember? Range compression done in the range direction through the match filtering technique is using the transmitted LFM and range FM rate. Okay, so first transmitted LFM we have to make, and range FM rate is given by the B by tau. In range cell migration correction, all target trajectory in the same range are transformed into the single target trajectory through the interpolation to make the trajectory straight. So, but in the RCM we have to do all the that pixel which have the same range, we are making it is a straight line. Okay, so that curve nature of the pixel points is transformed to a straight line which is parallel to the azimuth axis. Now, in azimuth direction of LFM pulses is constructed with the azimuth FM rate. After the azimuth compression done in the range direction through match filtering technique using the LFM having the azimuth FM rate. Okay, so now we have to construct the azimuth FM rate. It's given by this one, and we have to multiply in the azimuth direction, and then after we have to take the inverse FFT. So in this way, we have to do the SAR data processing. So basically in the SAR data processing, which we are using the pulse compression technique, means we have to multiply our range reference function with the data in both in the range and with the azimuth direction. In the range direction, the SAR parameters are given, means bandwidth of the signal is given and pulse width are given. Then we can calculate the range FM rate. But in the azimuth direction, we have to estimate this effective velocity in the azimuth direction, and R0 it is given. So our focusing and in the azimuth direction is very much dependent on how the SAR parameters are derived from our mathematical modeling. If we are not able to estimate properly, then our data will not be properly focused and it will give the blur images. Okay, so these are some of the basic concepts of the SAR data processing. Okay, so now I will show some one demo of the signals, SAR signals. So actually this is the one application which is developed by the IIRS Dehradun. So this is the application just to show the how the SAR parameters looks like and how we can derive. So, first we have to read some of the SAR parameter. Means in any SAR processing of the SAR data, we have one image data and one of the auxiliary file which is containing the SAR parameters. Okay, so first we will read some of the SAR parameters. Okay, so we will read one pulsar satellite data parameters. So the SAR parameters what we have read, satellite is the pulsar antenna length, it is given by 8.1 meter. Wavelength is given by the 0.2 meter. Sampling frequency, it is 32 megahertz. Pulse width, it is given by 27. Pulse bandwidth is 28. PRF, it is given by 2169 hertz. And slant range is given by 2842 kilometer. And satellite height is 687 kilometer, and satellite velocity is given by this. Okay, and squint angle, we will say it is giving a zero Doppler, means it is having the zero squint angle. So these are some of the parameters which are available in the data. Using this parameter, what we can do, we can process the SAR data. So first I will simulate one point target, means how the data is simulated. Okay, so first I have read the SAR parameter, and now I will calculate some of the SAR parameters. So based on this parameter, what we have calculated, the PRI, range resolution. Okay, the range resolution, the formula is C by 2B. So on substituting, it is giving around the range resolution 5.3 meter. Now azimuth resolution is given by, for the RAR case, it is given by L lambda by R. So 24 kilometer it is coming as a azimuth resolution. But after using the synthetic aperture concept, it is giving the azimuth resolution of L by 2. Okay, so L by 2 antenna length is this one. So synthetic aperture length, synthetic aperture concept making the azimuth resolution as 4.05. So this is the azimuth resolution, and synthetic aperture means what is the synthetic aperture it is forming in kilometer, means it is forming a 49 kilometer synthetic aperture length in the space. And it is because the synthetic aperture is very much larger, so we are getting the better azimuth resolution, which is given by 4.05 meter. So and the range per sample is given by the formula of Fs into the tau. So number of range samples is given by 864, which is Fs into tau. Fs is the sampling frequency. Pulse width is given by this one, tau. Azimuth per sample is given by this formulation. Now Doppler centroid is, since it is zero, then Doppler centroid is zero. Base Doppler is also zero, and Doppler ambiguity is also zero. So now we can generate the linear frequency in the real direction. So this is the real part. Using this SAR parameter, what we have done? We have generated the linear frequency modulated signal. The real part we can generate, and this is the imaginary part we can generate. And this is the phase. Okay, so this is the phase, unwrapped phase, and this is the frequency, and this is the frequency. Okay, so we have these parameters, pulsar parameter. Now what we will do, we will try to simulate one point target. So first we will form one synthetic point target, means we will have the range sample, azimuth sample. Now the how much range sample it is coming, 864, and azimuth sample it is coming around 7000. So what we will make, we can make around 8K sample, 8192 samples, a range sample, and 8192. Means we are simulating a scene which have in the range direction how many pixels? 8K pixels, and azimuth direction 8K pixel. Why we are taking 8K? Because our azimuth pulse is greater 7000. So we will take 2 to the power n, means around that 8K samples we are multiplying. So and now we are generating a point target in this way. So this is one 8K by 8K signal, and you can say a point target means a point target is put in this form, and it is having some energy. Now if the SAR will look this point target and it will transmit and the LFM, then this LFM will convolve with this target, and with the motion of the SAR, one raw data will be simulated. Now we will try to simulate the raw data. Means we will generate the range LFM, then azimuth LFM, and we can do the raw data simulation. So what is raw data simulation? Means this point target is convolving with the range chirp and the azimuth chirp, and forming a raw data. So you can see if a point target is like this, and the SAR will look this point target, then this type of raw data we will look. Okay, so this is the synthetic synthetic SAR simulation. Okay, from the point target we have make the one raw data using a single point target. So single point target, it is means the LFM in the range direction and LFM in the azimuth direction. So the target signal is expanded in both the direction, in the range direction, in the azimuth direction. Now in the range direction, you can see it is having the lesser samples, because number of the range sample is around A64. So the expansion in the range direction is lesser, but in the azimuth direction is greater, because number of samples in the azimuth chip is 7,000. Okay, so now this is the SAR raw data which we have simulated. Now what our main aim is to focus this raw data using our SAR data processing. In our SAR data processing, what we have to do, we have to now make the range match filter. Means we have the LFM, we have to take the complex conjugate in the range direction and azimuth direction, and in the azimuth direction we have to do in everything in the frequency domain. So first we have to generate a range match filter in the range direction and azimuth match filter in the azimuth direction. Then what we have to do, SAR focusing. So it will take time to because it is processing the raw data, and then it will again make a synthetic point target. Means what we have done in the simulation, means a high point target will be in the center. So this way we have some focused the target. Okay, so initially what we have done, we have put the target at this point. Then what we have done, we have simulated, we have multiplied, we have convolved in the range and azimuth direction. The data is look like this. And after that, we have done the this range match filter and azimuth match filter. We are doing the match filtering. Then the dark data is again focused. Okay, so and this is our scenario. Means first we have generated the point target, then we have generated the SAR raw data, and then what we have done, we have done the SAR focusing. Okay, now we can see some of the images. So this is the raw data. So this is the raw data, but it is in the form of data. It is a pulsar data. So after range compression, how the data looks, means we have done just in the range direction. So this is the data after the range compression. So it is not focused. Okay, so after that what we have to do, azimuth compression and RCM correction also. So after that, the final product is how it will look. So this is the focus data. Okay, so this is the overall SAR raw data processing. Okay, I will end now.